Hi everyone. Today we're going to talk about chords of circles. So a chord is a line segment whose endpoints lie on a circle. So here's a chord right here. So I have my circle centered at P that goes through Q, and here I have chord AB. Now, every chord determines an arc. So there's a chord here, and of course there's minor arc AB that goes with it. And in fact, every arc determines a chord. So you could actually think about this first being arc AB and then chord AB being determined by that arc. So this relationship between arcs and chords is the sort of first thing we're going to talk about in circles. So I have this chord. I'm going to construct a congruent chord to this also on this circle. So here I'm going to construct a circle with center and radius. So I'm going to put the center here. And I happen to know that the segment AB has a length F. And that gives me this circle. And so I'm going to put a point here, point D. And then I'm going to hide this circle. And now I can construct this segment. And this chord right here, CD, is congruent to chord AB because these are constructed to have the same length. So the first thing I want you to notice is that these two chords being congruent determine congruent arcs. And so this is the first theorem we're going to prove about chords and arcs in a circle. In a circle, congruent chords determine congruent arcs, and vice versa. In a circle, congruent arcs determine congruent chords. Now the proof of these two theorems, or it's really one biconditional theorem, relies on a strategy that you basically always use in circles, and that is when in doubt, just draw in radii. So I'm going to draw in all four of these radii. Now because all of these radii are congruent, we know that we have two isosceles triangles. Now, if the chords are congruent, then the two triangles are congruent by side, side, side. These angles will be congruent by CPCTC, and then these arcs will be congruent because they have the same measure and they're in the same circle. So if the chords are congruent, then the arcs are congruent. Now, vice versa, if the arcs are congruent, then these angles are congruent. They're central angles, and so congruent arcs in the same circle have the same measure. Now the triangles are congruent by side, angle, side, and then the chords will be congruent by CPCTC. So this is the first basic theorem about chords and circles, and that is congruent chords determine congruent arcs, and vice versa. Congruent arcs determine congruent chords. Now, probably the most important theorem, I'm just going to delete all of this stuff. The most important theorem about circles and chords is the following. I'm going to draw a line through the center of the circle, and that creates a very special chord, of course, called a diameter. Now, a very special and a very important theorem says that if a diameter passes through the midpoint of the chord, then it is perpendicular to the chord. And this is also a biconditional theorem. If the diameter is perpendicular to the chord, then it passes through the midpoint of the chord. So essentially the theorem says a diameter bisects a chord if and only if it's perpendicular to the chord. So this is just a theorem about diameters. The proof of this relies on the same strategy. Construct the radii to the endpoints of the chord. Again, we have an isosceles triangle. And now we can use facts about isosceles triangles. In an isosceles triangle, if the line from the vertex to the base passes through the midpoint, then it's also perpendicular. By side, 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 these angles are congruent. This is a linear pair, and they're congruent, so these are right angles. It's perpendicular. If it's perpendicular, then these two triangles are congruent by hypotenuse leg, and these two segments would be congruent by CPCTC. So that's the proof that if a diameter is perpendicular to a chord, then it bisects it, and if it bisects the chord, then it's perpendicular. So these are the two important theorems about chords in circles.